we start with it. So in this section here, again, we are going to do a comparison study with the data types. We compare Intel x86 with the ARM architecture, their data types. So hopefully by the end of this chapter, or by the end of this lecture, sorry, we will understand the basic data types supported by both Intel 86 and also ARM architectures. Also, we compare how data is represented and stored in both architecture again. Then explain how data alignment and the size affect performance. Then we identify the differences in instruction handling for various data types. Yeah. So here we can say that what is a data type? Actually, let's start with that definition first. A data type defines the form and also the size of data that a processor can recognize and manipulate. Now, in computer science or computer programming, we can say that data type set the boundaries of the data from negative infinity to positive infinity. And also it tells us the type of data, whether, for example, is it a character or decimal number or a whole number. Now, what I mean by boundary that is that in arithmetic college algebra, when we talk about real values or any values, we don't have no boundary. It can be negative infinity to positive infinity. But computer science or programming, memory, earlier time, memory were very expensive, very scarce resources. So we set boundary. We don't want to have a memory all the same size. I have a 1 billion value. I'll use the same size if I have only 20. We have to set a boundary. So that's why, for example, we have a byte short. Byte is the lowest for integer. Let's say Java. Byte will be the lowest data type for a whole number in Java, which means it's 1 byte. Short, I think, is 2 bytes. Then we have integer 4 bytes. Then we have long 8 bytes. I think 16. You say 8 or 16, somewhere around there. But long is the biggest. I can't remember the range of integer will be somewhere negative 2 billion and something to positive 2 billion something. So basically what I'm trying to say is that we use the data type to set the range, the bound, or I'll say the range rather than say the boundary, and also the type of data also. So that will lead us to the importance of data type. Determine how data is stored, and also how we can access it and process it, and the type of operation we can even perform on the data. Example, integer, floating point, character, and Boolean. They may have different operations. Most programs, as we mentioned, like Java, byte, well, we don't use word, maybe short, double, but then we have, as the assembly language, single, double precision, character, Boolean, etc. So the purpose of data here, we say, defines how much memory is used. I think that's the main key. As we said, setting the boundaries in the values will tell us the memory. The integer tell us what the memory size should be. Long memory size is bigger than short, like say in Java. Yeah. So that's all we can mention here. And the last thing I can say about data type also is that it influences the instruction format, also register usage, and then memory alignment also very important. And as we said earlier, integer, data type, floating point, decimal values, character, and Boolean. We can even have also vector, which is used for para data operation, like SIMD concept also, yeah. So that's the main purpose of a data type. Now let's go. As we said earlier, this session is more or less we compare differences with Intel 86 architecture and also the ARM. So we start with the Intel 86. So first thing we mention here will be the CISC. CISC. So first of all, it's Intel company, so developed by Intel, and it's more used in PCs and servers. And also it has a complex instruction set computing design. So it has a rich set of instructions and also variable instruction lengths. We said earlier, the reduced instruction, the length, the instruction length is short, is phase. So sorry, I'm going to say short, is phase. And CISC, as we said earlier, previous, is again variable. The size can be from 16, 32, 64-bit, etc. Also, the concept of backward compatibility for Intel system, Intel architecture use backward, which make sure that the new system still can work on the old system. Or backward compatibility ensure that older software runs on a newer CPU. Yeah, I think that's the best way. Older software run on a newer CPU than saying that the new system, what kind of system, we don't know. Yeah, so that's the idea here. Backward compatibility, support legacy, old system, 16-bit and 32-bit mode also. Okay, so that's all the generalization here. So Intel, again, we are in Intel x86 data type. You can see the byte, the size, the name, the common name we use, and then description. Again, this is ISA, instruction set architecture, not high-level language like Java or something. So you can see that byte word, double word is 32, then quad word is 64 bits, then 10 bytes is 80 bits, which the name already tells us the size. We know a byte is 8, so 10 bytes will be 80. Yeah. And we call it T byte. Double word, we call it D word. It can be integer or it can be a pointer also. Yeah. So let's wait for a few seconds. There's nothing much to explain here. The only thing we mentioned earlier about the SIMD, which stands for the single instruction, multiple data. It's kind of the extension allow a single instruction to operate on what multiple data element, a vector, which vector simultaneously. Intel supported Intel x86. Actually, this is very crucial for or important for graphics, multimedia, scientific computing, like the SIMD, yeah, single instruction, multiple, yeah. So let's wait for a few seconds if any question here. Okay, so if no question, let's move on to the next slide. We're almost done. I'll be looking at my time with my cell phone around here since I'm on a slideshow. I shouldn't miss the time. Well, now we are 3:57. So we should finish this section before take attendance. Okay, so the next, again, Intel x86 supports signed and unsigned integers. This is very straightforward. So 8-bit register, 16-bit register. It has a 32-bit register, like in Excel. I mean, this will be the assembly language for Microsoft platform. We use AL, AX, ES, depends on the size. So 8-bit, 16-bit, 32-bit registers. Yeah. Then the next is also handled by the x87 FPU. FPU stands for, again, floating point unit. FPU, yeah. Handle the floating point arithmetic using 80-bit stack also. Yeah. So that's an example of a data format here. 32-bit single precision float, 64-bit double precision double, 80-bit, which we call the T-byte extended precision. So also used for scientific and graphic computation, as we said earlier also. Yeah. Again, we're still on Intel x86. So data alignment with Intel x86. Here we say that it can refer to how data is arranged in memory according to its size, the alignment in memory according to its size. So typical alignment rules would be, let's say, byte. In byte, there's no alignment restriction. Then we have a word, which is 2 bytes, and you have a 2-byte boundary. I think the DW also, yeah, the 4 bytes. So you have 4-byte boundary. Then we have QW also. This data type all are used in assembly language also. Yeah. So here we say align accesses are more faster, or I'll say are faster, faster because they match memory boundaries a lot. Then unaligned accesses are allowed, but they are more slow performance. So misaligned can cause a performance penalties also. Yeah. So next we go to the introduction to ARM architecture. ARM, as we said earlier, stands for Advanced RISC machine. So you use the RISC architecture. So here first we say focus on simplicity and also efficiency. Dominant in mobile, mostly used like in mobile, IoT, Internet of Things, and also embedded system. Embedded system uses, because again, embedded system is a small computer, a special purpose computer. So we don't want large, compressed, a lot of instructions. So kind of use more, reduce instruction, make more reasonable. So it uses load store architecture also. So arithmetic operations occur only between registers. And also this means memory is accessed only what? Through explicit load store instructions also here. So we have the ARM data types overview here. And we can see each with their sizes. So integer can be A1632 and up to 64-bit. Floating point can be 32-bit for single and 64-bit for double. Then we have the vector. So here we have the SIMD data type here also for neo instructions also. So this is handled by the neo extensions. Then we have the Boolean types. So SIMD, as we said earlier, single instruction, multiple data. Then Boolean type can represent, of course, true, false. That's it. So normally we say that the ARM instruction set is more regular and compact, which simplifies compiler again design also, we can say. Yeah. Okay, so if no question, let's go now. So this is ARM integer data types. We have a byte, half word, word, double word from 8 to 64-bit. So 8-bit is the character or small integer. 16-bit is medium integer. 32 is standard integer. Then 64 be larger integer. So what 32-bit will be integer like regular integer in Java or C. That's 4 bytes, I think. 4 times 8, 32, yeah. Then double word will be like long or double word, yeah. Which will be 8 bytes. Yeah, 8 bytes. 8 times 8, 64-bit. Okay, let's keep going. So ARM floating point data types also. This is supported through the vector floating point and neo extension. And we can see the format either single precision or double precision. As we said earlier, single precision means up to like 7 decimal point or so. 64 will be up to 15 decimal places. Yeah. Then let's see the next one, which will be the alignment. I think we finish with all the integer and float. So data alignment also. So here we say ARM enforces the natural alignment. Natural alignment. So byte is 1 byte boundary, half word 2 byte boundary, word is 4 byte boundary, and then double word is 8 bytes. The advantage of this is that, again, we will come back to, I'll say here, simplifies the memory access logic. Yeah, memory access logic. Also, it improved the data throughput. and also reduce the CPU cycles. Misalignment also is the same as Intel x86. There's a penalty for misalignment for ARM, same as x86. So some ARM architecture allow it majority with performance penalties majority. Older version may even raise exception that's error during the execution of the program, so that can halt the executions. Yeah, so that's all we can say here. If no question, let's move on. So that's the comparison between the Intel x86 and the ARM. So in terms of the architectural type, as we said earlier, Intel x86 have more instructions, CISC, complex instruction set compute. Then ARM use reduced instruction set. Then we have a bandwidth will be 8 to 80 bits, here 8 to 64. The register count is fewer and more versatile for x86 Intel, but ARM is more general purpose. Then the floating point, we have x87 SSC AVX and VFP, and alignment is optional, but there's a performance hit. Here we say strict natural alignment. Okay, so these are some few examples. This example, again, as we said earlier, you can see based on assembly language. So this example of Intel x86, we can see what we are doing here. We are moving. We have first one, we have 8-bit. The second is 16-bit. And the third is 32-bit. And those are using assembly language, we see, normally we don't write a bit, but if I say move EASC, I know EASC extension is 32-bit. AX is regular, AL is the low 8-bit. Yeah. Now with ARM example also, we can say move RO, R1, R2, and we still have 8, 16, 32-bit for each one. So, this is just an integer representation. Then we have the floating point example also. Or wait for a few seconds to see if we have any question. Okay, let's keep going then. But one thing we can say here is that both perform similar operations, but they use different instruction, naming and register set. But both the ARM and Intel, the same operation they perform. We can say move. Just the naming also different. Then the same thing applies to the performance implications we have. So let's look the first one. Data type choice affect, of course, the execution speed. Also, the memory usage, or here we say memory footprint. Then power efficiency also. And then the compiler optimization, I'll say the RISC design allow better instruction pipelining than x86. x86 also can handle, we said earlier, is varied sizes with more complex decoding, whereas ARM is fixed. So that's all we can say here. Let's see, to summarize everything. Again, there's no any new theory here. We just compare. I think we went through the concept here already, the data type. Yeah, we just compare the x86 with ARM. So kind of comparing CISC with RISC. Yeah. In terms of instructional set architecture, the data type. Yeah. So that's all we can say here. Unless we wait for a few seconds. So we have some 2 or 3 question discussion, but we don't have no time. So that's the objective here. Intel x86 and ARM data types, the comparison. So if no question now, I'm going to stop this recording.